Good morning. My name is V. Selvam, Assistant Professor, Mechanical Engineering. Now I discuss about the advanced IC engines. The Unit 1 Spark Ignition Engines. Air fuel ratio requirement and various stage of combustions, normal and abnormal combustion, factor affecting knock, fuel injection systems, for monopoint, multipoint, and direct injection combustion chambers, effect of compression ratio, introduction to thermodynamics analysis of combustion process. First, discuss about the air fuel ratio or mixer requirements. An engine is generally operated at different loads and speeds. For this, proper air fuel mixer should be supplied to the engine cylinder. Then fuel and air are mixed to form three different types of mixers: chemically correct mixer, rich mixers, and land mixers. Chemically correct or correct mixer is one in which there is just enough air for complete combustion of the fuel. For example, to burn 1 kg of octane completely, 15 uh, 12 kg of air is required. Hence, chemically um, correct air fuel ratio for C8H18 is 15,12 is to 1, usually approximately to the 15 is to 1. This chemically correct mixture will vary only slightly in numerical value between different hydrocarbon fuels. It is always computed from the chemical equation for complete combustion for a particular fuel. Complete combustion means all carbon in the fuel is converted to CO2 and all hydrogen to H2O. The mixer which contains less air than the diametric requirement is called a rich mixer. The mixer is contains more than the diametric requirement is called land mixer. Automatic air fuel ratio requirements. Ideally, mixture must be enriched. Crushing mixture must be learned. High power mixture must be enriched. There are three stages of combustions. A typical theoretical pressure crank angle diagram during the process of combustion A to B, combustion B to C, and expansion C to D in an ideal four-stroke spark ignition engine. An ideal engine can be seen from the diagram. The end pressurized during the combustion takes place at a constant volume, that is at DDC. However, in an actual engine, this does not happen. The detailed process of combustion in an actual SI engine is described below. Then first stage A to B is referred to as the ignition leg and preparation, which phase in which growth and development of self-propagating nucleus of flame takes place. This is a chemical process depending upon both temperature and pressure, the nature of the fuel, and the proportions of the exhaust residual gas. Further, it is also depends upon the relationship between the temperature and the rate of the reactions. The second stage, B to C, is a physical one and it is concurrent with the spread of the flame throughout the combustion chamber. The starting point of the second stage is where the first measurable rise of pressure is seen on the indicator diagram. That is the point where the line of the combustion departs from the compression line, point B. This can be seen from the deviation from the motoring curve. The starting point of the third stage is usually taken as the instant at which the maximum pressure is reached on the indicator diagram, that is the point C. The flame velocity decreases during this stage. The rate of the combustion becomes low due to lower flame velocity and a reduced flame front surface. Since the expansion stroke starts before this stage of combustion, with the piston moving away from the top dead center, there can be no pressure rise during this stage. The next normal combustions. Under ideal condition, the common internal combustion engine burns the fuel air mixer in cylinder in orderly and controlled fashion. Then abnormal combustion, when the unburned fuel air mixer beyond the boundary of the flame front is subjected to a combination of heat and pressure for certain mm, duration, denotion may occur. Denotion is the characterized by the instantaneous explosive ignition of at least one pocket of the fuel air mixer outside of the flame front. A local shock wave is created around each pocket and the cylinder pressure may rise sharply beyond its descent limits. The next, knocking. Knocking is spark ignition ICE engine occurs when the combustion of the air fuel mixer in the cylinder start off correctly in response to ignition by the spark plug. But one or more pockets of air fuel mixer explode outside the envelope of the normal combustion front. The air uh, fuel charge is meant to be ignited by spark plug only and at a precise point in the piston stroke. Knock occur when the peak of the combustion process no longer occurs at the optimum moment for the four-stroke cycles. The shock wave creates the characteristic metallic pinking sound and cylinder pressure increases dramatically. Effect of engine knocking range from inconsequential to completely destructive. The factor affecting the knocking. There are three factors affecting the knocking. First one, density factors, second one, timing factors, then third one, composition factors. First is density factors, the compression ratio. The compression ratio of the engine is an important factor which determines both the pressure and the temperature at the beginning of combustion process. Increase the compression ratio, increase the pressure and the temperature of the gases at the end of the combustion stroke. This decreases the ignition leg of the end gas and thereby increase the tendency for knocking. The overall increase the density of the charge due to higher compression ratio, increase the free flame reaction in the end charge, thereby increase the knocking tendency of the engine. The increase in the knocking tendency of the engine with the increase in the compression ratio is the main reason for limiting the compression ratio to the lower value. The next one, mass of the indicated charge. The reduction in the mass of the indicated charge into the cylinder of a engine by throttle by reducing the amount of supercharging reduce both the temperature and the density of the charge at the time of ignition. This decreases the tendency of knocking. Then inlet temperature of the mixer. Increase the inlet temperature of the mixer makes the compression temperature higher, thereby increasing the tendency of knocking. Further volume efficiency will be lowered, hence the lower inlet temperature is always preferable to reduce the knocking. Temperature of the combustion chamber walls. Temperature of the combustion chamber walls play a predominant role in knocking. In order to prevent the knocking, the hot spot in the combustion chamber should be avoided. The retarding the spark timing. By retarding the spark timing from the optimized timing, that is having the spark closer to TDC, the peak temperature are reached further down on the power stroke and are thus of lower magnitude. This might reduce the knockings. The power output of engine. Increase in the output of the engine decrease the temperature of the cylinder and the combustion chamber walls and also pressure of the charge, thereby lower the mixture and end gas temperatures. This reduces the tendency to knock. Time factors. The turbulence. Turbulence depends on the design of the combustion chamber on engine speed. Increase the turbulence. Increase the turbulence, increase the flame speed, and reduce the time available for the end charge to attain the auto ignition condition, thereby decrease in the tendency to knock. Engine speed. And increase the engine speed increase the turbulence of the mixer considerably, resulting in increase the flame speed and reduce the time available for free flammable reactions. Flame travel distance. The knocking tendency is reduced by shortening the time required for the flame front to um, traverse the combustion chamber. Engine size and the spark plug position are the three important factors governing the flame travel distance. Engine size. The flame required a longer time to travel across the combustion chamber of a large engine. Therefore, larger engine has a greater tendency for knocking than the smaller engine, since there is more time for the end gas to auto ignite. Hence, the spark ignition engine is generally limited to size of about the 150 bore. Time factors. Combustion chamber shape. Generally, more compact the combustion chamber is, the shorter in the flame travel and the combustion time, and hence better anti-knock characteristics. Therefore, the combustion chambers are made as spherical as possible to minimize the length of the flame travel for a given volume. If the turbulence in the combustion chamber is high, the combustion rate is high, and consequently combustion time and knocking tendency are reduced. Location of spark plug. In order to have a minimum flame travel, the spark plug is generally located in the combustion chamber, resulting in minimum knocking tendency. The flame travel can also be reduced by using two or more spark plug in case of large engines. The third one, composition factors. Air fuel ratio. The flame speed are affected by air fuel ratio. Also, the flame temperature and reaction time are different for different air fuel ratios. Act and volume of the fuel. The high self ignition temperature of the fuel and low free flame reactivity would reduce the tendency of knocking. Generally, paraffin series of hydrocarbon have the maximum, and aromatic series in the minimum tendency of knock. Then combustion chambers. The design of combustion chamber for SI engine has an important influence of the engine performance and its knocking tendency. The design involves the shape of the combustion chamber, the location of spark plug, and the location of inlet and exhaust valves. Because of this importance, the combustion chamber design has been a subject to considerable amount of research and development of in the last 50 years. Thank you.